Welcome to Lecture 5. Last time I discussed several examples of the double coset formula, and I gave a list of those properties that we learned about the natural operations on the equivariant homotopy groups of orthogonal spectra. So these operations are, on the one hand, the restriction homomorphisms associated to continuous homomorphisms of compact Lie groups, and then the transfer homomorphisms that come from closed subgroups of a larger compact Lie group. I ended with a precise packaging of all these natural operations into a category, and this is where I want to take off today. So as I already explained last time, the global Burnside category that I will denote by A is the pre-additive category whose objects are all compact Lie groups, and where the abelian morphism groups of morphisms from G to K are given by the set of all natural transformations from the functor pi 0G to pi 0K, where both are considered as functors from the category of orthogonal spectra to the category of sets. Equivalently, you could also consider them as functors to abelian groups that would give you the same results, and in particular, such natural transformations are automatically additive. What I want to start discussing today is how we can actually calculate this abelian group in a very explicit way. I already wrote down the result at the end of the last lecture, and I will repeat that explicit calculation in due time, but not now. So the calculation has two ingredients. The calculation of the group AGK has two ingredients. So the first one is that this functor pi 0 upper G is actually representable in the sense that I will make precise today. So it's represented by the orthogonal spectrum sigma infinity plus of B global G, so the unreduced suspension spectrum of an unstable object that I call the global classifying space of G, and I will explain what this is today. And then the second ingredient is that we can explicitly describe the zeroth K equivariant homotopy group of the representing object. And then it's essentially an instance of the Yoneda lemma that will tell us that natural transformations biject with this abelian group of K equivariant homotopy groups of the suspension spectrum of B global G. I recall from the first lecture that blackboard bold L, which is a little bit hard to write here, or boldface L is the category of linear isometries. Linear isometric embeddings. So the objects are what I call inner product spaces. They are finite dimensional vector spaces over the real numbers, equipped with a scalar product. And the morphism spaces L of VW is the Stiefel manifold of linear isometric embeddings from B into W. So this is a topological category, so we can look at continuous functors out of it to spaces and orthogonal spaces. Are just continuous functors from L to T, which is my notation for the category of spaces, and that was defined to be compactly generated spaces, which includes the weak Hausdorff condition. In the first lecture, this category L was just a stepping stone in defining a different indexing category whose functors out of which are orthogonal spectra. But actually, this category of linear isometric embeddings and the functors defined thereon, they have a life on their own in global homotopy theory, because they actually represent unstable global homotopy types. In this class, I will mostly focus on stable phenomena, so I will keep the discussion of unstable global homotopy theory to a minimum. I will just tell you enough so that all the stable statements make sense. But since this is an important theory on its own, I want to give you some pointers to the literature here and tell you other things that this is connected to. The orthogonal space model that I'm using here is discussed in detail in chapter 1 of global homotopy theory. In particular, there you will find a definition of global equivalences in this unstable context that I will not formally introduce in the class here because we don't need it in general. There are various other models for unstable global homotopy theory, and I want to mention two of them. So one model is the L space model, where L is what I like to call the universal compact Lie group, just that it's neither group nor compact nor Lie. So technically it's the topological monoid, the contractible topological monoid of linear isometric self-embeddings of R infinity. And I call it the universal compact Lie group because it contains copies of every compact Lie group in a very precise sense, but I'm not going to go into this here, but I'll just show you where you can read about it. Yet another model for unstable global homotopy theory is the Orbi space model, which is originally due to Gettner and Enriquez. And this is the connection between unstable global homotopy theory and the global homotopy theory of Orbi spaces and Orbi folds and topological stacks. So Orbi spaces is really something that you can think of the quotient of a topological space acted upon by some compact Lie group, and you want to retain the homotopical information, but you also want to remember a little bit more than just the orbit space. You want to remember information about the isotropy group. And Orbi spaces are one way of making this precise. So I think this is a very interesting story. In particular, it gives you a way to represent genuine cohomology theories on Orbi spaces, Orbi folds, and topological stacks via orthogonal spectra, via stable global homotopy types. So time permitting, I might get back to this later in the class, but right now I just want to leave you with these references. So here's an important example of an orthogonal space, namely the global classifying space of a compact Lie group. So let G be a compact Lie group. Now we have to make a choice. We choose a faithful G representation. We usually call this faithful G representation V, and as always this means it's a finite dimensional orthogonal representation of the compact Lie group G. In this situation we can form an orthogonal space. This I call the global classifying space. B sub global of G is the following orthogonal space: L V blank modulo G. So I should explain what this is. So L is this indexing category, this topological category. So we're taking the represented functor of maps out of V, linear isometric embeddings, out of something into something that varies, and always out of the V. Because V is a G representation, G acts from the left on V, and this gives you a right action when you map out of it. Because the action of G was assumed to be faithful on V, this action on the mapping space out of V will actually be a free action, and that will be convenient for various things that we do. A couple of more comments about this. I do not record the V, this chosen faithful representation, in the notation for the global classifying space. And the reason for that is that the unstable global homotopy type of B global G is actually independent of this faithful representation. I cannot tell you what this precisely means because I don't want to introduce global equivalences of orthogonal spaces, but we will see some hint of that a little bit later on one of the next blackboards. Alternatively, you could also say that you choose this representation, and then whatever I will do with it, whatever I will prove about it, will work with whatever choice of V you made, as long as the choice is faithful, as long as G acts faithfully on it. Orthogonal spaces represent unstable global homotopy types, and the philosophy is that an unstable global homotopy type is supposed to be a collection of K homotopy types, where K runs over all compact Lie groups, and there should be some consistency in these K homotopy types built into the theory when you change the group K. I want to now tell you how you can actually access this K homotopy type when you are given an orthogonal space. So here's how this goes. That Y be an orthogonal space. And K a compact Lie group. And then the underlying K space of this orthogonal space Y is the following space. I write Y of UCK. So UK was my notation for the chosen complete K universe. And on the face of it, this doesn't make sense because that's something infinite dimensional, and an orthogonal space only takes values on finite dimensional inner product spaces. So we simply define this as the co-limit over the values at all finite dimensional sub-representations over the complete universe. So this is also a notation I had used previously when defining the equivariant stable homotopy groups. This is the post-set of finite dimensional sub-representations, and I let this run over all W, and I just take the co-limit in the category of spaces that I'm working with. So for every orthogonal space, this gives you a K space, and the way to think about global equivalences of orthogonal spaces is that you want a morphism to induce a K weak equivalence on this K space for all K. So this definition is almost the right one, but not completely, so there's one small caveat. It's the correct definition whenever the Y, the orthogonal space, is what I call a closed orthogonal space, which just means that all the structure maps induced by linear isometric embeddings are also closed embeddings. All the orthogonal spaces that will come up and that I will explicitly talk about will have this property, so they are all closed orthogonal spaces. And that means global equivalences can really be tested as K-weak equivalences on these underlying K spaces. In complete generality, the definition of global equivalences is a little bit more complicated, and you can read it up. All right, in particular, the underlying non-equivariant homotopy type is the value of Y at R infinity, simply because R infinity, an infinite direct sum, the co-limit over the Rn's, is a complete universe for the trivial group. So let's look at these underlying K spaces a little bit for the global classifying space of a compact Lie group G, and let's see what we get. So the first observation is that because G acts faithfully on V, because G acts faithfully on V, if I look at L, V, U, C, K, this has two commuting actions, one action by G coming from the source variable and one action from K coming from the target variable that commute with each other. So this has a free G action, and it's non-equivariantly contractible. Now, after all, this is an infinite, if you ignore the K action for the time being and the G action, this is an infinite dimensional Stiefel manifold, and these are contractible. It also has the structure of a K times GCW complex. It admits the structure of a K times GCW complex. So in particular, this cofibril is a K times G space, and taking orbits is something meaningful and something homotopy invariant. So for example, if I take L of V, R infinity, so if I take K to be the trivial group, this is a contractible GCW complex, non-equivariantly contractible GCW complex with a free action. So if we divide out the G action, so this is what the non-equivariant homotopy type represented by the global classifying space would be. This is just a classifying space in the non-equivariant sense for the compact Lie group G. in the usual sense. It's a classifying space for G. And actually there's a more general statement that I will write down for you and then overlay a reference, and that's the following theorem. So let G and K be compact Lie groups. And then there's this implicit choice of faithful representation that I'm not recording in the notation here. And then the K space, I take the global classifying space of G. That's just an orthogonal space. The G action is already used up. I evaluate it at the complete K universe. This is now a K space. And of course what this was is we took linear isometric embeddings into the complete K universe and we divided out the G action. And this is a classifying space for KG principal bundles or KG bundles. So these KG bundles are G principal bundles over K spaces. And I give you a reference for this statement. This is my reason for calling this the global classifying space, because it's a single global object that encodes these kinds of classifying spaces for principal G actions, but for all compact Lie groups in a uniform way at the same time. Let's make the abstract definition of the global classifying space a little bit more concrete by looking at some explicit examples. This time I want to start with a trivial example, namely that of the trivial group. Then we can choose the representation to be the zero representation. So the trivial groups with one element are the only ones where the zero representation is faithful. Otherwise, you always have to take a non-zero representation. And then, if we look at the definition, the global classifying space of G, so the global classifying space of the trivial group, you take linear isometric embeddings out of the zero vector space. The group is trivial, so nothing we have to divide out. And of course, the zero vector space has exactly one linear isometric embedding into every other one in the zero map. So this is the constant orthogonal space with 1 point. Constant 1 point orthogonal space. Which is also the terminal orthogonal space. So we already knew that the 1 point space is a classifying space for the trivial group, and the point here is that there's no global direction added to this, it's just constant. But as soon as we take a non-trivial group, things become a bit more interesting, and there's a genuine global direction to the story. The things won't be constant anymore. So let's look at the next complicated example after this. So this is where G is a cyclic group of order 2, for which I will just write C. So this is cyclic group of order 2. Now we have to choose a faithful representation, and of course there are many, and it's probably a good idea to choose the smallest one that we can think of, and that would be the sign representation. This is faithful. This is the sign representation on R. One-dimensional. Okay, so let's see, first of all, before we divide out the action, what we get. So we have to take linear isometric embeddings from the sign representation into something varying. Let's call this W. This is one-dimensional. So we can evaluate at the element 1, and we land in the unit sphere. So this sends a linear isometric embedding from the sign representation into W to the value at 1, which is a vector of length 1, and this is the unit sphere of W. And of course the sign action here on the source corresponds to the integral action on this side. So now we can pass two quotient spaces on both sides, and we get a homeomorphism from the global classifying space of the cyclic group of order 2 at W onto the unit sphere modulo of the integrative action. This is the projective space of W, the space of all lines. And in particular, we can pass the colimits. You know, this works on both sides in the same way. So if we evaluate the global classifying space of a group with two elements on a complete K universe, we get the projective space of this K universe with the action that it gets from the universe. The group moves the lines around, and that gives you a K action on the projective space. A little bit more general example, which nevertheless works in exactly the same way, is when we take the orthogonal groups. So suppose G is ON, the n orthogonal group. For n equals 1, we would get the previous example back. So then we would take as our representation Rn with a tautological action, which is faithful, with a tautological of n action. And then in this situation, we can look at linear isometric embeddings out of Rn into W, modulo the action of On. And we get an n-plane in W by taking the orbit of such a linear isometric embedding and just sending it to the image, the phi of Rn, which is an n-dimensional subspace of W, so this is the Grassmannian of n-planes in W. So in this sense, the global classifying space for the orthogonal group, which is what this is, the global classifying space of On evaluated at W, is just a functor of taking Grassmannians of n-planes, which non-equivariantly you probably knew that this is a model for B On. Of course, if you chose a different faithful representation, you would not get the Grassmannians up to homeomorphism. So, sometimes it's a little bit of an art which faithful representation to choose. For some you might get a more understandable answer than for others. And again, something that you might have seen before is now we take the global classifying space of On and we evaluate it at a complete K universe, and then we just get the Grassmannian of n-planes in the complete K universe. And just as non-equivariantly, this is a classifying space for principal On bundles over K spaces, and then by passing to frame bundles, this is also a classifying space for rank n equivariant vector bundles over K spaces. Let me give another perspective on what the global classifying spaces classify, and then also deduce a corollary that I will need later when proving the representability property for the 0th G equivariant homotopy groups. So for this discussion, I need the notion of a graph subgroup. A graph subgroup of K times G. K and G are the compact Lie groups that we're considering. Is a subgroup of the following form. It's gamma alpha, where gamma stands for graph. It's all pairs J alpha of J, where J is in J. For some continuous homomorphism. Alpha from J to G, and what is J? So this is defined on a closed subgroup of K. Defined on a closed subgroup J of K. So there are two parameters. On the one hand, the closed subgroup J of K, this homomorphism is only partially defined, and the continuous homomorphism itself. So equivalently, if you have a subgroup in K times G, this is a graph subgroup. If and only if, first of all, it's closed, and on the other hand, if you intersect it with 1 times G, this only consists of the identity element. So this is a nice little exercise. So for example, you can get the group J back by projecting delta onto the first factor. Now I'm going to use also some background for the class, namely if you have a topological group and a family of closed subgroups, that there always exists a universal space for this family. So this is a cofibrant G space, or if you want a GCW complex, that is characterized by the property that first of all the stabilizer groups belong to this family that you're considering. And also if you take fixed points for anything in this family, then you get a contractible space. In particular, we could look at the group K times G and this family of graph subgroups, and we could wonder what a classifying space or a universal space for this looks like. And now the point is that these spaces that come up in the global classifying spaces of G are exactly examples. So more precisely, I consider linear isometric embeddings from V into UK. This is the chosen faithful G representation, and this is the complete K universe. I claim that this is a universal space, a universal K times G space for the family of graph subgroups. So I will not explain why this is a cofibrillant K times G space. You can actually give it a K times G CW structure if you want, and I want to gloss over this. Let's look at what the fixed point spaces look like. So because G acts faithfully on B, G acts freely on the mapping space. And that exactly means that all the stabilizer groups satisfy this property. So this is one part of what we have to justify for being a universal space. So all stabilizer groups are actually graph subgroups. Of K times G. The other property is that if we take the fixed points of such a graph subgroup, we get a contractible space. So how does this go? Let alpha from J to G be a continuous homomorphism. And J is a closed subgroup of K. So now we have to look at the space of linear isometric embeddings with the G action coming from this factor and the K action coming from this one. They commute with each other, and we have to take fixed points by the graph of alpha. Well, this is something we can rewrite as follows. I can take linear isometric embeddings from alpha upper star of V, and this means it's the J representation where J acts through this homomorphism and the given G action, and then into UK, and then we can take just J fixed points of the whole thing. So that's exactly the same. Now I'm going to use a bunch of properties that I will not justify. So one thing that I've already mentioned a little bit earlier is if you have a complete universe for the big group K and you restrict it to a closed subgroup, then you get a complete universe for that subgroup. So the implicit restriction to J that I'm not recording in the notation gives you a complete J universe. Another property is that complete universes were defined by the property that any finite dimensional representation admits an equivariant isometric embedding. So the defining property of a complete J universe is that this space is non-empty, but this space is then actually always contractible if this is a complete universe. And that's something I don't want to prove here, but just use. So in particular, this is a contractible space, and altogether this verifies this claim that this is a universal space for the family of graph subgroups. Let me draw an important consequence from this. So let's consider another G representation. So let W be another G representation. And this one doesn't have to be faithful, so V is, but W doesn't have to be. Then we can take the direct sum. Then V plus W is another faithful representation because V is faithful. Another faithful G representation. So then we can look at the restriction map. So this time I'm not restricting an action, but I'm restricting a map to some subspace. So I look at the space of linear isometric embeddings from V plus W into UK. And I go to the space of linear isometric embeddings only from V into UK. And the map sends a linear isometric embedding and it restricts it to the first summand. So let me just abbreviate this as restriction to V plus 0. So what do we know about this map? So first of all, it's K times G equivariant. And source and target are universal spaces for the same family. same family of subgroups, namely the graph subgroups. Of K times G. And then, universal spaces are defined so that they are unique up to equivariant homotopy equivalence, or more precisely, any equivariant map between universal spaces for the same family is necessarily an equivariant homotopy equivalence. So in our situation, this means that the restriction map is a K times G homotopy equivalence. The restriction map, so this one that restricts to the first summand, is a K times G equivariant homotopy equivalence. And that means we can pass to G quotients. So in general, passing to orbit spaces is not necessarily homotopical unless you make some assumptions on these spaces. But passage to orbit spaces is certainly compatible with actual homotopies and hence with homotopy equivalences. So let's do this. I go from linear isometric embeddings from V direct sum W into UK, and now I divide out the G action. And again, I get this restriction map to linear isometric embeddings from V into UK divided by the G action. So before the G and the K action commuted, we divided out one of them, we still have the other one. So this is a K equivariant homotopy equivalence. So this, incidentally, is essentially the proof that the global classifying space is independent up to global equivalence of the choice of faithful representation. Well, what else do we have to do? So this is the value of the global classifying space based on the choice of V at K. This is the global classifying space based on a different choice, V plus W. And this particular K equivariant map comes from the morphism of orthogonal spaces where you let this variable run. So modulo the fact that global equivalences aren't exactly the things tested on underlying K spaces, but they almost are, and they are in this example. So modulo this slight caveat, this is showing that this particular restriction morphism of orthogonal spaces, where you let this variable run, is a global equivalence. And then if you have two faithful representations, V and V prime, you just compare them via going through the direct sum in the middle, which projects to both of them. So this is showing that the global classifying space is up to global equivalence independent of the choice of representation V. Let me draw one more consequence for easier reference in the later application. So this is a K equivariant homotopy equivalence, and in particular, if I now take K fixed points, so I go from linear isometric embeddings from V plus W into the complete K universe, I first divide out the G action, and then I take K fixed points, and I do the same thing here. I do linear isometric embeddings from V into UK. I divide out the G action, and then take K fixed points, and this is now just a non-equivariant homotopy equivalence. So this last thing is something to be kept in mind for later purposes. The zeroth G equivariant stable homotopy group is represented by the suspension spectrum of the global classifying space. I've just told you all sorts of things about the global classifying space, and now I will tell you how you turn an orthogonal space into an orthogonal spectrum. So this is the following construction. An easy generalization of the suspension spectrum of just a space. So let X be an orthogonal space. And then the suspension spectrum, or more precisely the unreduced suspension spectrum, X doesn't have a base point, sigma infinity plus of X, is the following orthogonal spectrum. With the following values. So I have to tell you what is the unreduced suspension spectrum at an inner product space V. And you take, first of all, the thing you would always do for a suspension spectrum, the one-point compactification of V smash. And now we take the value of X at V at a disjoint base point and smash them together. So that's the value. The actions of the orthogonal groups, O of V is diagonal from the action here and from the action here, which comes from the fact that we have an orthogonal space. So what are the structure maps? So the structure map sigma VW, which goes from SV smash sigma infinity plus XW to sigma infinity plus X of V plus W is the following map. So on the left hand side we will have SV smash SW smash X of W, and we have to get to SV plus W smash of X V plus W. And let me be a little bit sloppy and write isomorphism on the first vector, so that's the preferred homeomorphism from this smash product to the one-point compactification of the direct sum. And here we take the value of the orthogonal space X at some particular linear isometric embedding, and I is the embedding of the second summand, W to V plus W is the embedding of the second summand. So in the last term I talked a lot about suspension spectra of spaces or of G spaces, and that's of course a special case. If the orthogonal space happens to be constant, it always takes the same value, and on morphisms it's the identity map, then this just reduces to the suspension spectrum, or the unreduced suspension spectrum of a space. So while we are at it, I would like to mention that the suspension spectrum functor has an adjoint. So the functor is sigma infinity plus going from SPC. So I will use this notation SPC for the category of orthogonal spaces. To the category of orthogonal spectra, for which I use the notation SP. This has a right adjoint. This is a version of the underlying infinite loop space that I denote omega bullet. So let me define this. So the value of omega bullet Z. So Z is an orthogonal spectrum. Omega bullet Z is an orthogonal space. Add an inner product space V is the following. Omega bullet Z of V is maps, based maps from the one-point compactification of V into the value of the orthogonal spectrum at V. I also have to tell you what the structure maps are. So a linear isometric embedding phi from V into W induces the map. So now I have to give you a map phi lower star so that this becomes a functor from map star SB X of V to map star SW X of W. So this is a construction that you've already seen earlier when we discussed equivariant stable homotopy groups. I start with a based continuous map like this. I have to send this to a new based continuous map, and what I do is the following. So I write W as the sphere of W minus the orthogonal complement of V. Again, this is not the set theoretic complement, it's the orthogonal complement, smash S of V. Then I take the identity on the first smash factor and F on the other one. This gets me to SW minus SV smash X of V. Then I use the structure map sigma W minus phi of V comma V to get to X of W minus phi of V, direct sum V, and then I use the effect of X on a particular isometry to get back to W, and then I have to close the parentheses. So one thing you have to be slightly careful with is I just wrote an isomorphism sign here and here. Of course I'm using a particular isomorphism, namely the one which is the inclusion on this summand, and it's given by phi on the other summand. This is kind of important because phi could be an isometry, and then you would basically be looking at conjugation by phi. So this is a stabilization construction that already came up in the discussion of equivariant stable homotopy groups, and now it's the structure map making this into an orthogonal space. Of course, an adjunction, if we're really serious, should be more than just the two functors. I should tell you either the unit or the co-unit of the adjunction, and let me do this for the unit in this case. The unit of the adjunction, so this should now be a morphism of orthogonal spaces. If we start with the x, it should go from x at v to first taking sigma infinity plus of x, then taking omega bullet of that, and the whole thing at v. So I have to give you such a continuous map for every inner product space v, and then I will leave it to you to check it's actually a morphism and it actually is the unit of an adjunction. But I just want to tell you that this is reasonably explicit. So on this side we will get not SV, we get maps. Maps from SV into the value of the suspension spectrum at V, which was SV smash x of V plus. And you know it's the most obvious map. It sends little x in here to the map that sends V to V smash little x. So it really comes from an unstable adjunction between loops and smashing with a V sphere and suitably modified to fit into this. As I said, I will omit the verification that this is an adjunction. Now we know what a global classifying space is and what its suspension spectrum is. To properly state the representability property, I only have to tell you what the universal homotopy class is. So here it is. The stable tautological class that I denote EG, and it lives in pi 0 G equivariant of the unreduced suspension spectrum of the global classifying space of G. And this is the class represented by the following G map. So I take the one-point compactification of SV. So V is this faithful representation that we have chosen and that's not reflected in the notation. And I go to SV smash L of V comma V mod G plus. So this is exactly the value of the unreduced suspension spectrum of L of V blank modulo G at V, because we just have to plug in the V here and also smash with the sphere. And of course there is a very tautological map here, that's why I call it the tautological class. We just send V to V smash and then the orbit of the identity. This is clearly a G equivariant map, so it represents a zero-dimensional G equivariant homotopy group. And now I can properly state the representability theorem. I state it in a little bit more general form than we'll need it for the calculation of the Burnside category. So here's the theorem. So let phi from the category of orthogonal spectra to the category of sets be a functor that takes global equivalences to bijections. And then evaluation at the stable tautological class is a bijection between, on the one hand side, the set of natural transformations of functors from orthogonal spectra to sets from pi 0g into this functor k to the value of the functor at the representing object, sigma infinity plus of b global g. And we send tau, which is a natural transformation, from pi 0g to phi to the value at the stable tautological class. So that means we take the value, first of all, of the natural transformation at this particular orthogonal spectrum. This is now a map from pi0G equivariant of the suspension spectrum of the global classifying space of G. In there we have just defined this element, and so we evaluate this map on the element, and we exactly get an element in this set, and the claim is that this is a bijection. So this is the main result of today that I will prove. But let me first draw the corollary that we want, and this is the corollary where we simply take phi to pi 0 k, which by definition takes global equivalences to bijections, so it applies to this, and then we get a bijection between A of gk, the morphisms in the Burnside category, which are exactly the natural transformations by definition, to pi 0 k equivariant of sigma infinity plus of the global classifying space of G. So this is kind of half of the calculation of the morphisms in the global Burnside category. And then starting with the next class, I will tell you how we're going to calculate this, but this is an important reduction. For the proof of the theorem that I will now present, we will need the following proposition. So let G be a compact Lie group. Be a faithful G representation. And W any G representation. And then we have already before looked at a certain morphism of orthogonal spaces. And the restriction morphism. Which goes from linear isometric embeddings from V plus W into a varying second argument, modulo G, to L of V blank modulo G, which is, both of these are models for the global classifying space because this is also faithful, and this induces an isomorphism of K geometric fixed points homotopy groups of suspension spectra for all compact Lie groups K. So this is what we'll really show, but then the important consequence is the following corollary of this, in particular the morphism from the unreduced suspension spectrum of this orthogonal space, linear isometric embeddings from V plus W modulo G to sigma infinity plus linear isometric embeddings only from V into G. This is a global equivalence. So how do we get this in particular? Well, by definition, to be a global equivalence, we would have to check that we have isomorphisms on all genuine equivariant homotopy groups and all integer gradings. But you know, at least in the context for finite groups from last term, that if you want to check isomorphisms on equivariant homotopy groups of a group and all its subgroups together, you might as well check isomorphisms on the geometric fixed point homotopy groups for the groups and all its subgroups together. You cannot do this individually, you always have to take all subgroups at once. This works in pretty much the same way in the context of compact Lie groups. I'm just going to use this. And then in the global context, it really means that alternatively, instead of checking isomorphisms of equivariant stable homotopy groups, we might as well check isomorphisms of geometric fixed point homotopy groups, as long as we also check this on all compact Lie groups. So this is how we get the in particular, and on the next whiteboard I will show the argument for the first claim. I need to show that the restriction of a linear isometric embedding to the first summand, which is assumed to be a faithful G representation, induces an isomorphism on the geometric fixed point homotopy groups for every compact Lie group K. So let's just rewrite these geometric fixed point homotopy groups on the right hand side a little bit differently. So phi n k of sigma infinity plus L of V blank mod G. Let's first recall the definition. So this is a colimit over finite dimensional subrepresentations, k invariant subrepresentations of the complete K universe. That's this K. And then we're not taking equivariant maps from the W sphere, but non-equivariant maps from the fixed point sphere. And then there's also an Srn, which is this dimension n. I guess I'm only doing it for non-negative n, because for negative n's both sides are 0 anyhow, or you could just modify the argument. So here we're taking maps from the K fixed points of W. And now we're taking maps into the value of this at W and then fixed points. But that we can rewrite right away. This will be S to the WK smash and then the fixed points. L of V W modulo G and then the K fixed points. And all together we're taking non-equivariant homotopy classes of base types. And you should recognize this expression from something that we have done a little bit earlier. It might not be immediately obvious how we can apply the corollary that I proved a little bit earlier, but this goes as follows. So we use a cofinality argument to rewrite this colimit over W in a double colimit. So I can take the colimit over W in S of U K, and then a colimit over U in the same poset of finite dimensional K invariant subrepresentations of the complete universe. And here I can take maps from Rn, direct sum Wk, SWK. Now I take maps from V into U and not W mod GK. And I'm using that this is a filtered poset, so the diagonal is cofinal, and instead of running over W and U, we could only run over the diagonal entries, and that would give us an isomorphism. So now we use compactness of the sphere. So this is a compact space, and we're going to take a colimit of maps into something. In this variable, all the structure maps are closed embeddings, and so if you map something into a sequential colimit over closed embeddings, you know this has a cofinal sequence, so the colimit is actually sequential. If you map a compact space into a sequence in the colimit of a sequence of closed embeddings, then it always lands in some finite stage, and the same with homotopies. That means you can move this colimit inside here. So this is actually the colimit over W in S UK, and then maps from S Rn plus WK into S WK smash linear isometric embeddings from V, and now we have the complete K universe inside modulo G and then K fixed points, and I guess I should have written a disjoint base point everywhere. Based maps. And this of course is nothing but the non-equivariant nth homotopy group of the suspension spectrum with the disjoint base point of this space V into UK modulo G and then the K fixed point. So these are the non-equivariant stable homotopy groups of some non-equivariant space. You take this universal K times G space, mod out the G action, and then K fixed points. But then of course we're done, because I can run the same argument with V plus W instead, and I've showed a little bit earlier that we get a homotopy equivalence on K fixed points of G orbits, whether we do the V or the V plus W here. So this shows, using this isomorphism, shows that that map is an isomorphism up here. So that's the end of this little lemma, and so we know that the restriction morphism gives us a global equivalence when we pass to suspension spectra. Now we have all the necessary ingredients to prove the representability theorem. So here's the proof that evaluation at the stable tautological class is a bijection from the set of natural transformations from pi 0 g into a functor phi that's assumed to take global equivalences to bijections, to the value of phi at the unreduced suspension spectrum of the global classifying space of G. So I want to show the injectivity in detail and then tell you what you have to do the surjectivity. And for the injectivity, I will tell you how the value at a general orthogonal spectrum and a general homotopy class is determined by the effect on the stable tautological class. So let's take a natural transformation. So let tau from pi 0 g to phi be a natural transformation. And we also have x an orthogonal spectrum. And we consider any class in the equivariant homotopy groups in pi 0 g equivariant x. That's where the natural transformation starts from, and this is represented by a map represented by a G map f from S W to x of w. This is what elements in zeroth equivariant homotopy groups look like for some G representation w. So now we're going to bring our faithful representation V into the game by simply suspending with it. So then suspension or stabilization from the left, which is the G equivariant map from S V plus W to x of V plus W. It's again a G equivariant based continuous map. There's another representative for the same class. So from this unstable map, we can now make a morphism of orthogonal spectra. So let V diamond F flat from sigma infinity plus L of V plus W blank modulo G to X be the adjoint morphism of orthogonal spectra. So I guess I should elaborate a little bit what exactly I mean by the adjoint morphism. I'm putting two adjunctions together. So morphisms of orthogonal spectra from sigma infinity plus of L V plus W mod G into X. So there was this adjunction that I discussed between unreduced suspension spectrum and this omega bullet, this global version of the underlying infinite loop space. So that gives us a bijection to morphisms of orthogonal spaces from L V plus W blank modulo G into omega bullet of X. So now if there wasn't this orbits by G, we would be looking at morphisms out of a representable functor, and then the Unidar lemma would tell us exactly that without this we would have the value of this orthogonal space at V plus W. And now, of course, orbits in the first variable just get to fixed points in the second variable. So by the Unidar lemma, this is isomorphic to omega bullet of X at V plus W, and then G fixed points on the whole thing. And this just spells out to G equivariant maps from S V plus W and to X of V plus W using the definition of the omega bullet X. And that's exactly what we have. We have a G equivariant map. So we have an element in here, and this is what I mean by the adjoint morphism on the other side. So this adjoint morphism has a specific property. This satisfies, and you can check this property by directly looking at the definitions, expanding all the definitions. So it's a morphism. I can take its effect on zeroth equivariant homotopy groups. I evaluated at the stable tautological class, and now let me be a little bit more precise. I mean, usually I have suppressed the chosen faithful representation in the notation for the tautological class, but now I want to emphasize it because I use the class based on V plus W and not on V, which is an element in pi0G equivariant of this. And this will just go to the class F that we started with. You just expand out all the definitions and how the junction works, and this is what you get. So, wonderful. So we have started with a class, we've produced a morphism of orthogonal spectra, now we can exploit the naturality of tau. So we get a commutative diagram which looks as follows. I have pi0G equivariant of sigma infinity plus L of V blank modulo G. Here I have pi0G equivariant, sigma infinity plus L of V direct sum W blank modulo G. So here I just write isomorphism. So that's this restriction morphism that we discussed before. You restrict a linear isometric embedding to the first sum in V. And I explained on the last whiteboard why this is a global equivalence, so we get an isomorphism on G equivariant homotopy groups. So here we have the morphism V diamond F, and what it induces on equivariant homotopy groups. This goes to pi0G of X. And in here we have the class EG, but based on the faithful representation V. So here we have the class EG V direct sum W, and here we have the class F. And by expanding the definitions, you can see that this class goes here, and this class goes here, and this is an isomorphism. Now we have this natural transformation tau, and we can write the values at the various orthogonal spectra down. So this is the value of tau at the orthogonal spectrum sigma infinity plus L of V blank modulo G. This goes to phi of sigma infinity plus L of V blank modulo G. Here we have tau for the orthogonal spectrum sigma infinity plus L of V plus W mod G. And here we have tau for the orthogonal spectrum X. So here we have the value of the functor phi at sigma infinity plus L of V direct sum W blank modulo G. Finally, we have phi of X here. And here we have the effect of this morphism on the functor phi. Correct sum F. So this diagram commutes. That's just the naturality of tau as a transformation. So this is an isomorphism because the restriction morphism to the first summand is a global equivalence. Now this is an isomorphism because we've assumed that the functor phi also takes global equivalences to bijections. Now if you contemplate this, then you can see that the value of tau x on the original class F, this class comes from here, that's an isomorphism, is completely determined by the value on the stable tautological class. So let me try to squeeze in that relation here on this side of the whiteboard. So the value of tau x at this class F is the same as phi applied to F V diamond F applied to phi of rho. So let me load this restriction map just by rho, then this would be pi0 G of rho, so I have a name for it, pi0 of rho inverse, it's an isomorphism, and then applied to tau for this spectrum, which I'm not going to write down, at the fundamental class EGV. So here we have this relation that the value of the natural transformation at an arbitrary orthogonal spectrum X and an arbitrary equivariant homotopy class is ultimately determined by just the value at the special orthogonal spectrum, the suspension spectrum of LV blank mod G at the stable tautological class. So this proves the injectivity. So let me just do the surjectivity in words and not write anything more on the whiteboard. So for the surjectivity, you basically turn this argument around. You basically use this formula to define the natural transformation. So, in other words, you start with an orthogonal spectrum X, you start with an arbitrary homotopy class, you represent it by some equivariant map, you suspend by the chosen faithful representation V, you pass to this adjoint, and then you define it by this formula. Of course, if you define it this way, you have to check that things are well defined. So you have to go through a bunch of arguments. So the first thing is, if you keep the same W but you vary F by a homotopic morphism, but this is relatively easy to check because this adjunction is enriched and it preserves homotopy. So if you replace F by a homotopic morphism, then this will go to a homotopy morphism of orthogonal spectra, and all these functors are homotopy functors. So for phi, this leads a little argument that the functor that preserves global equivalences in particular takes homotopic morphisms to the same morphisms. That's one of the things you will have to verify. So this way you check that it only depends on F up to homotopy, and then of course you could have a W prime that it's defined on, and you have to compare those. And this is another naturality argument that involves the compatibilities of these various tautological classes under enlarging the representation V plus W. I think you don't really learn that much more. If you've seen the injectivity part, you don't learn that much more by the surjectivity argument. And if you can't figure it out yourself, you can also read it up in the book. This ends the proof of the representability theorem, the statement that the zeroth equivariant G-equivariant homotopy group functor is represented by the suspension spectrum of the global classifying space of G. As I said, this is essentially half of the calculation of the morphism groups in the global Burnside category, and I would like to end this lecture here, and next time I will start proving the other half. Thank you for your attention.